Thank you so much. It was a very good introduction from James and Anna about the context of this workshop. Pleased to see several familiar faces. And so I hope this time can be interactive and the workshop can be productive. The title of my talk on the surface might seem to be slightly tangential to the content of this workshop, but it is deliberately done for a purpose because we will be discussing about the integrity of biometric data, the fairness of biometric data, because anytime we talk about explainability, we not only look at the decision process of the neural network, for example, we must also look at the data that is being supplied to the neural network or any other classifier based on which a decision is made. So hopefully this particular talk will conform to some of the expectations of this workshop. So I direct the iProbe lab at Michigan State University, as Pedro kindly provided that introduction. We have currently about 8 PhD students and 4 master's students, and we have graduated several students in the past. And you're welcome to visit us here at Michigan State. I think Adam Chaika has been here. Adam, have you been to Michigan State before? I don't recall. Maybe it's time to invite Adam for a special lecture here at MSU. So the reason
I was there.
Oh, you were there. Okay. Well, we'll re-invite you.
Happy to be there again.
Wonderful, wonderful. And looks like you are one of the program chairs of this event. So well done, Adam. So the research theme for our lab is across multiple topics and certainly focused on biometrics. And so in the context of biometrics, we are looking at 3 themes. One is adversarial biometrics, the other one is privacy, and the third one is fusion. And we all know what biometrics are and what biometrics is as far as definitions are concerned. The automated recognition of individuals based on their biological and behavioral characteristics. So we're talking about biometric traits, which means you need to be able to extract distinguishing and repeatable features. Many different biometric traits, and I'm sure we will encounter many of these traits in today's workshop. You have fingerprint, palm print, iris, voice, signature, face, DNA, conjunctival vasculature, ear, keystroke dynamics, dental biometrics, gait, hand geometry, vasculature biometrics, and other biometric traits based on some psychophysiological properties as well. Many different biometric applications ranging from healthcare in order to keep track of patients, to border security, to access control on personal devices. And so you can see that biometrics has a broad spectrum of applications, which include refugee services and access to ATMs and so on and so forth. So before we go into today's talk, we must start looking at the impact of altered biometric data. That means biometric data, let's say images that have been subtly modified. What are the consequences as far as biometrics is concerned? So here is some work from Dong et al. They presented this in CVPR 2019. They talked about 2 black box attacks. One called as the dodging attack, which you see at the top, and the other is the impersonation attack. Now, what is the dodging attack? Well, you see 2 images, and I hope you can see my pointer as well. You see 2 images, and these are of the same person. And so obviously you want your biometric system to successfully match these 2 images. But it's possible to subtly modify this image in such a way that you now generate a new image, and this new image will not match with this image on the left. So in other words, you have sent some queries to the biometric system, and it's a black box attack, so you don't know the specifics of the biometric system, in this case, the face recognition system. but you're able to generate an image that looks very similar to this image that you see here, but nevertheless cannot successfully match with this image. Now, you can also launch a different kind of attack where you now see two images, and these two images are of two different people. But now you can transform this image into this image in such a way that this image is now modified as this, but it can successfully match with this original image here. In other words, this image will not match with this image, as it rightly should not, but then this generated image can actually successfully match with this image. So this obviously poses a problem to biometric systems because with some subtle modifications, which are perhaps not discernible by the human eye, maybe discernible by automated machine learning systems, but certainly not easily discernible by the human eye. What happens now is you're obtaining results that are contradictory to what is expected. Now, this kind of attack is not confined to the digital mode. It can also go directly into the physical world. And many of you might be familiar with some work from Carnegie Mellon University and other universities as well, where you can create face masks, like the one that you see here, this face mask. Now, when this face mask is placed on this person, so it's in the physical world, then surprisingly, this image is matching with this image as far as a specific face matcher is concerned. So this particular artifact is created based on an understanding of the face matching system. But here, what you observe is that imposing this glass on this person in the physical world can lead to a false match with this specific target image. There are other issues also with let's say, person detection systems. And these problems are exacerbated in the context of neural networks. And many of you are familiar with adversarial attacks that can be launched against a neural network-based classifier by making very subtle modifications to the input image, but obtaining radically different output results. So here, for example, you see there are two individuals and you have a neural network-based detector. And I'm not sure if it's very clear to you, but the detector is able to detect this person, but not this person. And obviously that person is upset, or maybe they're not upset, I don't know. But the reason why this person is not being detected is because of this artifact, an image that has been tied to this individual, affixed to this individual. And so the system is able to detect the person, is able to detect the chair, but not able to detect this particular individual. But now, when that artifact is moved about, you can see that this person now is successfully detected. And the person is now trying many different poses with respect to that artifact. And as you can see, this particular image here has caused the neural network to misbehave. This is where we have to consider both the instability of neural networks and also the integrity of the data that is being supplied to these systems. And so in the context of biometrics, clearly, this is a very realistic problem. There is a widespread use of Photoshop filters, Snapchat filters, where face images are modified, mostly for entertainment purposes, but can potentially be used for other nefarious purposes as well. And secondly, there are many deep learning-based manipulations that can do attribute transfer or attribute modifications. You can start out with an individual who has, say, facial hair, and you can now generate a new image in which the person does not have facial hair. You can even change, presumably, the age of the subject as far as visual appearance is concerned. You can change the color of the hair, or you can change the expression of the mouth, and so on and so forth. So this is a realistic problem. When images are modified, you want to be able to detect that. And in some cases, modifying the image is acceptable, as we will see in this particular lecture. So this brings us to the field of image forensics. And as much as we talk about explainability and interpretability, as James pointed out in his opening comments, we must at the same time discuss the integrity of the data by using image forensic schemes. So in this regard, many questions can be asked. I'm showing some iris images here, well, really ocular images, and the iris is a part of it. You can ask a question such as, which sensor produced this image? And by using techniques such as PRNU, photo response non-uniformity, you can potentially answer that question if you have a closed set of sensors available. Or you can ask the question, is this an altered image? Visually, it looks like an altered image, but is it an altered image? Or you can ask a question such as this, given the set of 4 images, how are these images related? Photometrically and geometrically, not identity-wise. We assume that they pertain to the same identity, but now the question is, how are these images related from a photometric and a geometric standpoint? These questions are pertinent because one needs to understand the integrity of the data that is being used by neural network classifiers or even just any other classifier. Another challenging problem is that of near duplicates. These are subtly modified images. And as the name suggests, they're near duplicates. So they look very similar. So for example, you have 5 images here, and these images have been derived from one of these images here, and they've been subtly modified. Or you can apply a gamma transformation, or even some subtle geometric transformations like rotation. So what you're observing here is a set of images that are related to each other and are merely subtle modifications of each other. Now, in some cases, the images may not match with each other, but in some other cases, the changes are made in such a way that subtly the image can start matching with a different identity. And so this is the reason why near duplicates in the visual sense can pose some problems. But the problem that I'd like to discuss, at least for the first few minutes, has to do with this phylogeny tree, which means you're trying to define the relationship between these near duplicate images. Again, the word near duplicate is important because they look very similar to each other, not in terms of identity, but just in terms of photometric content. So here you see 5 images labeled as 1, 2, 3, 4, 5. And the word phylogeny, which is clearly borrowed from genetics, is basically allowing us to create a tree-like structure, which tells us that image number 5 is the original image. So we call that as the root image. And from 5, you have derived 2, 3, and 4. And from 4, you have derived 1. So the set of 5 images, unordered, are now ordered in this fashion based on an algorithm that I will discuss shortly. So what happens here is you're able to identify what is the original image, and you're also able to state that 2, 3, and 4, images 2, 3, and 4 have actually been derived from 5. Now, we must note here very quickly that we are not using any of the meta information in the images because some cameras would produce some metadata or some EXIF data. We're not using those data points at all. We are using just the pixel intensities. In this case, it's a 3-dimensional being RGB. And so we are only using the pixel information in order to make these structures that you see here. What is the importance of the problem? Well, firstly, we would like to know whether a set of near duplicate images, they originated from a single source image, or if they originated from multiple images. The source image means the root image that I talked about in the previous slide. This can also be used to detect image tampering because one could say, well, this image has been modified from this other image. Perhaps there is a motive for that. You can't detect the motive, but you can detect the tampering. In some cases, you can actually determine what kind of transformation was applied in order to transform one image to the other. Is this a change in brightness? Is this a change in some histogram, or is this some kind of histogram equalization, or has the contrast been changed, and so on and so forth. So this really involves both image forensics and data analysis. And so this is explainability in a slightly different context. You're able to explain the changes that you're observing in images by applying some rigorous process. So to construct an image phylogeny tree, if you recall, that was the tree-like structure I showed in a previous slide, we have a two-step process. We call this as IPT, which stands for image phylogeny tree. This is a two-step process. Given 5 images, for example, the first step would involve creating a 5x5 matrix, which actually tells us the relationship through a single value between pairs of images. So for example, here, S11 doesn't make sense, so that's why the diagonal elements are left blank. But S12 is a measure which talks about the similarity between 1 and 2, images 1 and 2. And this will be different from S21, which is talking about the relationship between 2 and 1. Now, the reason why this asymmetric property is needed is because we have to know if 2 has been transformed to 1, or if 1 has been transformed to 2. And in some cases, both are possible. But in many of the applications that we're discussing here, we definitely need an asymmetric measure so that we can more reliably assert whether 2 has morphed to 1, or 2 has been modified to 1, or if 1 has been modified to 2. So that is this matrix. And once we get this matrix, then you can use a tree spanning algorithm, like a minimum spanning tree algorithm, to construct the image phylogeny tree. So much of the effort is in this step, the first step, which is computing this matrix. Because once we have this matrix, which is recording the asymmetric similarity or dissimilarity between pairs of images, once this matrix is available, then we can more easily and trivially generate the IPT. But what are the challenges for this particular problem? Well, first think about the large space of photometric transformations. You can apply brightness, you can apply contrast changes, you can apply something like a contrast limited, adaptive histogram equalization, gamma corrections, median filtering, Gaussian filtering, the list goes on. There are a large number of photometric transformations, and clearly we don't want to be modeling each one of them separately, because that will be a prohibitively difficult task. Not only do you have a large number of transformations, for each transformation, you can have multiple parameters. Let's take the Gaussian transformation, for example. There are at least 2 parameters that it depends on. One is the size of the window, and also the variance that is used to apply on the image. So you have 2 parameters, which is actually a very modest number, but you can think of certain transformation filters which would require a larger number of parameters. Not only do you have a large number of parameters, for each parameter, say for example window size, you have multiple potential values, 3x3 windows, or 5x5, 9x9, 13x13. So clearly you can see that if we were to start modeling each transformation, even if we knew the world of transformations, it is going to be a very challenging and prohibitively difficult thing to do. Finally, we need to be able to distinguish between A to B and B to A. Was A transformed to B, indicated by the red arrow, or was B transformed to A, indicated by the blue arrow? So all these things make this problem a very challenging one. So what is our approach? Well, we use a generic parametric transformation function to model the relationship between any 2 images. Again, generic parametric transformation function. The word generic is important, and the word parametric is equally important. So since we don't know the set of transformation functions that are being used, we just use a very generic form, as you will see shortly. So given 2 images, A and B, we will estimate the parameters of this function in both directions. Because these functions are parametric, as you will see shortly, we basically estimate the parameters when A is transformed to B, and then also estimate the parameters when B is transformed to A. And then we will use the likelihood of these parameters. So we're talking now about a multidimensional density function. So we use the likelihood of the parameters to determine which of the two cases is more likely. Is it likely that A was transformed to B, or was B transformed to A? So this is the broad set of steps involved in our algorithm. So this kind of summarizes it. You have two images, B and A. We have a generic transformation function because we don't know what the actual transformation function is. So we have a generic transformation function, which is denoted by T, and T is conditioned on alpha, which is a set of parameters defining T. And so basically we're estimating what set of parameters, alpha, would transform A to B. Once we have the transformation function, then you can use very simple techniques to estimate the parameters. So I'm not going to talk about estimating the parameters because there are some ways to do that either iteratively or using closed set expressions. So the first question is, what are these generic transformation functions that we're talking about? Well, we considered many different types of basis functions, polynomial functions, wavelet functions, radial basis functions. And for example, you can have a Chebyshev polynomial, you can have a Gabor wavelet, you can have a bump RBF, and so on. And so we considered a set of basis functions. And these functions were chosen because in the previous literature, these type of functions have been used to model images. And that was one of the reasons why we used these functions, because they have been previously used, not by us, but by other researchers in modeling images for very different purposes. So as you can see on the right-hand side, each of these functions has an expression, and there are some parameters pertaining to that expression. So that is the first thing. So let's use this view graph to explain what's going on at a very high level. You have two images. You can notice here A and B. And you can notice here multiple panels. Each panel corresponds to the application of a specific transformation function. Legendre, Chebyshev, Gabor, Gaussian, bump, and so on. So that's why you have multiple panels here. In each panel, the respective function is trying to model the transformation from A to B and from B to A. So if you use the Legendre polynomial, you can notice here that it is trying to create a B prime, which actually says that is how A is transformed to B. So when you do this transformation via this function and you estimate the parameters and then you apply the parameters, this is the output that you get. And you can see the disparity. That's because this function is not a very good function, but in some other cases, you can see that transformation is reasonably well modeled. We must keep in mind that these basis functions, or the transformation functions, were not selected based on our understanding of what the actual photometric transformations are. So for example, these functions were not chosen because we said, well, brightness is going to change, or contrast is going to change, or some kind of gamma correction is going to be made. Certainly not. These are very generic functions. And the goal of these functions is not necessarily to replicate exactly how B looks like or how A looks like, but merely to get the parameters that are estimated when transforming A to B or B to A. So that is the purpose of these functions. So this allows us to compute an asymmetric measure. I'm not sure if you remember earlier on, I said that you need an asymmetric measure to understand the relationship between two images, pairwise relationship. So now we model the transformation in both directions, resulting in two sets of estimated parameter vectors, right? You have two sets. we denote this as alpha and beta. So alpha would be in the forward direction, A to B, and beta would be from B to A. Next, we will compute the likelihood ratio, denoted here as lambda alpha and lambda beta, which is based on the probability distribution associated in the forward direction and in the reverse direction, and that of the parameter alpha. So here, lambda of alpha is basically taking a likelihood ratio. What is the probability of observing alpha, assuming it is in the forward direction, over what is the probability of observing alpha if it were in the reverse direction? Now, clearly, these probabilities are obtained by using a set of training data. So let's say you have 100 images or 1,000 images. You would apply a set of photometric transformations. And when you apply those photometric transformations, you get the transformed image for each of the input image. And so the moment you do that, you can use the same technique to estimate alpha and beta, and eventually you can estimate a density function. Now, again, avoiding some of the more intricate details, what is happening here at a very high level is this. When you're given two images, A and B, you estimate two sets of parameters, so alpha and beta are vectors. And then you take the likelihood ratio associated with alpha and with beta. Now, this gives us an asymmetric measure. And this asymmetric measure can then be used to construct the matrix, and then you use depth first search to construct the IPT, which is the image phylogeny tree. So we took an existing database and we generated over 2,700 IPTs by subjecting face images to a random sequence of 4 transformations. And so this resulted in 27,270 images. So here's one IPT, just one IPT. You notice here, this is 1, 2, 3, this is one IPT. So we have the ground truth. Now the question is, if we give these 10 images to our algorithm, will it be able to construct this tree? So that is the question that the experimental analysis would answer. There are 2 kinds of relationships, as you can see here. One is an immediate link, 2 is an immediate descendant of 1, or there can be an ancestral link, that 4 is not an immediate descendant of 1, but through 2 is a descendant of 1. So we have 2 kinds of links that we have to also assess. For example, 3 is not a descendant of 2. Similarly, 8 is not a descendant of 7, but 9 is a descendant of 3. All this is to say that there are 2 types of links that our algorithm wishes to deduce. So there are 2 metrics. One is the root identification. Can this method correctly detect the root? And the second metric is, can it correctly construct the IPT? So if you look at an existing method, its performance for root identification is 47%. And our algorithm, there are 5 graphs here because they correspond to the 5 sets of basis functions. And so what you notice here are 5 results plus the baseline, the existing method. And you can notice that the method is very competitive. It's not 100%, but it's 80%, because this is a very challenging problem. Similarly, the IPT reconstruction, if you use an existing algorithm, it's 18.75%, but one of our techniques results in 66%. Again, not a spectacular performance, but keeping in mind what the baseline performance is, the improvement is radical. We must reiterate that this is a very challenging problem. Anyone working in digital image forensics would say that. For multiple reasons. One is, you're not dealing with natural scenes, you're dealing with face images or iris images or fingerprint images. And all these images have common morphology. And so subtle changes cannot be easily detected. Secondly, the changes are subtle by definition, because that's why we have near duplicate, the term near duplicate images being used. And so the photometric transformations are subtle, and so this compounds the problem. The reason I'm making these observations is to suggest that these numbers, though not spectacular, are surprisingly very high compared to the baseline algorithm. surprising in the sense, not unexpected, but in terms of improving the performance over the baseline. Now I can use the word surprising correctly. Surprisingly, this technique also works on unseen modalities. In other words, you can train your algorithm on face images and then test it on iris images or even fingerprint images. The reason being, it is only trying to model the photometric transformation, not necessarily the content of the image as far as the modality is concerned. So for example, using the parameters, or rather the likelihood, parameters, namely the forward and the reverse probability distributions on face, and then applying it on iris, actually results in a root identification accuracy of 95% in the context of iris, and the IPT reconstruction accuracy 68%, which is very similar to what we had previously when we trained on face and tested on face. When you use other types of transformations, say, for example, Photoshop or deep learning based, then as you can see here, the root identification accuracy is close to 90% in the case of Photoshop, but the IPT reconstruction accuracy was much higher in the case of Photoshop. And in the case of deep learning based method, the reconstruction accuracy is 65%, which again is very similar to what you see over here. So the point here is that when we talk about the integrity of data and being able to model the data, being able to explain the data, I think there is room for much work, especially by harnessing image forensics scheme. And that is why I'm grateful to Anna and the team for inviting me to give this talk, because this particular problem is not well studied. And I look forward to seeing more PhD students engage in this very challenging problem because it has several applications, both in terms of explainability of data, but more importantly, in imparting image forensic capability to biometric systems. So there are many other types of data generation processes, deep fakes. All of you are familiar with this website, thispersondoesnotexist.com. The three images that you see here are synthesized images using GANs. One thing we try to do is generate images, generate audio data using a mechanism called DeepTalk, which we published about 2 years back. So let's assume you want to listen to the morning news through your smart speaker, but now you get to choose whose voice is narrating the morning news or the weather update or the audiobook. So the text comes from these sources, but now how do you ensure that it is being articulated and enunciated by the voice of your favorite newscaster? So we worked on this project for an organization called NAB here in the US. And so we have what is called as the DeepTalk encoder, which takes the target speaker, your favorite newscaster's voice, and it encodes it, creates an embedding of it. And now when the target text is provided, you see the target text here, it uses existing engines like the Tachytron and the Wave RNN, both of which are referenced here, in order to create a synthesized spectrogram and then to produce a synthetic voice. So for example, here is a news article here, and this is the original voice of a newscaster named Hannah, and with her permission, we are playing her voice. Now she's going to be narrating something not related to this news article, because this is her original voice. 5
new cases of the coronavirus were reported in Ingham County on Monday, bringing the total cases in the Lansing area to 1,017.
I'm not sure if you heard that. If one of you could confirm that the audio was discernible.
Yes, good.
Yeah, thank you, Jane. Now comes the generated voice of Hannah. And so this is not Hannah, but a DeepTalk generated voice. And now Hannah is actually reading this news article that you see here.
This all comes following a recent nationwide study by retail analytics company First Insight, found that malls ranked last among locations where consumers say they will feel safe shopping.
Now, I'm not sure how it came across in your computer, but if you use a biometric matcher, then the original voice will be matched with this generated voice, which is what we demonstrated in our paper as well. So similarly, we have another newscaster, Ted, and the same news article can be read out by Ted. And so here, when you're creating synthetic data, there are some benefits to it. The point is, in some cases, synthetic data is used for nefarious purposes. And in some other cases, potentially it is used for some beneficial purposes. And we have to distinguish between these two things. In other words, when we try to validate the integrity of the data, we must also keep the end goal in mind. And in some cases, the integrity of the data is deliberately being perturbed in order to create confusion. But in some other cases, there seems to be a legitimate use of that data. And so the use case understanding is very important. I'm taking a quick look at the time. I'd like to wrap this up very soon because I have one more topic to discuss as well. So I'll go over this very quickly, that is, so that we can come to the last part of the talk. This is work that we did several years ago, but which has regained some interest recently. And so that's the reason why I thought I could include it in today's presentation. Here, you're not talking about synthetic data, but you're talking about partial data. And so here's the original fingerprint, and you see portions of the fingerprint. And if you're using a smartphone, which is biometrically enabled, you will notice that if it is fingerprint enabled, that the sensor is very small because it's residing on the smartphone. And during enrollment, you capture multiple partial fingerprints. So which means the system is expecting you to place your finger multiple times, and each time it is presumably capturing a different part of your fingerprint. But all these impressions are partial. That is what you see here on the right. In some cases, the system will allow you to enroll multiple fingers. So you can first place your right index finger, and then when it asks you to continue placing your finger, you can now switch to the left index finger. So not only do you have multiple partial fingerprints, you can potentially have multiple fingers themselves being enrolled as the same identity. Now, access is granted to the smartphone when during the time of authentication, the partial fingerprint that you present to the system matches any one of the partial fingerprint that were offered during the enrollment time. So here the keyword is partial. And also the other keyword is any one of the partial fingerprint. Because most systems do not try to take these images in order to create an elaborate mosaic impression. They don't do that. They might, but most of them don't. What they do is they keep these as separate impressions. And so when you provide an input fingerprint, which is partial, it just has to match with any one of these. Then it is deemed to be a match. Now this poses a problem because one could create what are called as master prints. And these are fingerprints that match accidentally with a large proportion of the fingerprint population. And they could be either full prints or partial prints, although the problem is more conspicuous when you use partial fingerprints. So what is the problem here? Well, suppose you have identified 5 prints, and we call this as master prints because they are akin to a master key that can unlock any room, say in a building. And so that's why master print, because these fingerprints can potentially match with a large number of target users. Now we used this concept of partial fingerprints or master prints to develop what we call as deep master prints, which are generated using some optimization processes involving GANs and neural networks. So now we have a situation where on the top you see some original fingerprints, And on the bottom, you see these synthesized fingerprints. But the synthesized fingerprints are partial and fingerprints. Not only are they partial, but they're also master prints. And so they can match accidentally, within quotes, with a large number of target identities, which means if you convert these prints into an artifact, into a spoof, into a physical spoof, then potentially you can try unlocking someone's smartphone, because the chances of unlocking using these master prints is much higher than just using any random print. And just to see some numbers, let's assume that your fingerprint system is operating at a false match rate of 0.01%, false match, right, or 0.1% or 1%. If you use a single master print from our original paper, which was not generating it using GANs, this is the success rate. At 0.01%, the success rate is 1.88%. At 0.1%, it's 6.6. At 1%, it actually goes up to 33.4. In our original paper, we also used a set of 5 master prints. That means if the first one fails, we try the second one. If the second one fails, we try the third one. And there are 5 because in many phones, after 5 unsuccessful attempts, the phone will lock down itself. So if you use multiple master prints, then in our original paper at 0.01 FMR, it's 6.8. And if you can see at 1%, it is 77. But using a single deep master print, which is the technique that I alluded to here in a BTAS 2018 paper, you notice that the numbers are much higher, especially at 1% FMR. Remember, here we're just using a single deep master print, and the single deep master print was generated using a GAN. So the point here is that when you use synthetic data with some specific goal in mind, then this particular synthesized data can be used in order to attack a system. So you can say that this is a synthetic fingerprint, but then to identify it as a master print is a much more difficult thing. But in reality, a master print can cause much damage and much harm to the biometric system. So the final part of the talk is on soft biometrics. And in particular, we're going to talk about how modifying an image can actually be beneficial in some cases. So this is slightly older work, but in the context of this workshop, I thought it would make sense to present this. And so I've included this as the last part of today's talk. So many of us know the term soft biometrics. You're talking about attributes such as gender, age, ethnicity, or health, which can be automatically derived from the face image. So you're talking about a trained classification system or a trained regressor, which when applied to an input image can actually assess these soft biometric attributes. And this can also be done for other non-obvious biometric traits such as iris, where given an iris image, you can develop an attribute classifier. And the attribute classifier can produce a report like this, saying that the subject is likely to be a male. The image was taken using an A optics camera. The iris stroma is plain textured, or even something about the pupil, that the pupil is highly constricted, suggesting strong ambient illumination. So in other words, using a single image, you can deduce, using image forensic schemes, some attributes of this image, not only attributes of the image, but attributes of the person, not only attributes of the person, but also attributes of the sensor that was used to acquire the image. And so this is what makes this very interesting, because on one hand, this can bridge the gap between human and machine description of data. If I tell you that this iris is 010010001, it probably will not make much sense to a human reviewer. But if you provide a report like this, it might make more sense to a human reviewer. So extraction of soft biometric traits actually bridges the gap between human and machine descriptions of data. But on the other hand, this can compromise privacy. And this is where the danger lies. Because some could say, well, I gave my ocular image or iris image in order to gain access to a secure facility. But I didn't expect the individuals to use that data in order to profile me, right? So there are some concerns revolving around the automatic extraction of these attributes. Many of you might have heard of this face to gene application, where given a face image, one could actually predict genetic ailments potentially associated with that face image. And there are some benefits, clearly. As you can see in this small report here, a patient was not diagnosed for a long period of time, but this application was able to make an assertion within a few minutes, whereas the doctors took 16 years before they could say what was wrong with the person. So the point here, again, is that given an image, a single image, you're now able to extract information far beyond what was perhaps intended. And this poses a risk to privacy. As deep learning-based methods become more prominent and more popular and more widespread, then you can begin to potentially glean information that you previously thought was not present in the image, or that you previously thought could not be extracted. And so clearly there is a huge risk here of compromising someone's privacy. So this brings us to the topic of controllable privacy. And more specifically, what we would like to do is to take an input image and then transform it into an output image in such a way that certain attributes are retained and other attributes are confounded. So for example, we take this input image and using an autoencoder, you create the output image in such a way that this output image can be used successfully by a face matcher, but cannot be successfully used by a gender classifier. So the gender classifier is confused, whereas the face matcher works. And so we call this semi-adversarial networks. For obvious reasons, semi-adversarial, it's not fully adversarial because it is still allowing the face matcher to work, but it's not allowing the gender classifier to make assertions correctly. And all we do is just modify this input image in a very subtle way. So the way it works is, let's assume you're in some image space and you see two categories. And just for this discussion, let's assume that these are two age groups, for example. What semi-adversarial networks do is that they mix these images. Each point is an image. And so you can see that the red and the green points are now not easily separable, whereas here they were linearly separable on the left. On the right, they're kind of mixed. But somehow the identity information is preserved, which means images of the same subject, they occur close to each other in the transformed image space, but then the two clusters denoting, say, two different age groups are mixed in this new image space. So that's what a semi-adversarial network is doing. It consists of a convolutional autoencoder. And the trick lies in the training stage. So when this autoencoder produces an output image, this output image is supervised by what we call as an auxiliary face matcher, and also by an auxiliary, in this case, gender classifier. It can be any other attribute classifier. We are using gender classifier as an example because these type of classifiers have been widely described in the literature. So you have supervision from this auxiliary face matcher and the auxiliary gender classifier. We use the word auxiliary because during training, you can use a specific face matcher and a specific gender classifier, but during testing, you're not obliged to use the same face matcher that you see here, nor the same gender classifier that you see here. So these are labeled as auxiliary in that they're only used during the training stage. So a simple autoencoder supervised by two classifiers, one being a face matcher and the other being a gender classifier. And what these two are doing is the face matcher is ensuring through its loss functions that X prime matches with X, whereas the gender classifier is supervising X prime in such a way that the gender label of X prime is different from the gender label of X. Now we can impart multi-attribute privacy, where you can take an input image, produce an output image, with certain labels in place, gender, age, race, for example. You can see that gender, age, race. So here you can give the input image, and you can also specify what kind of target attributes are needed. But the way this is different from any other type of attribute transfer network is that the identity information has to be preserved. That's the challenge here. And that's the point of note. You can change, for example, the gender, the age, and the race, but you still have to retain the identity label. So I won't go into the details, except to point out that besides the auxiliary classifiers that are used during the training stage for supervision, there are also specific loss functions that we employ, including a reconstruction loss, in order to impart this functionality that I talked about. So I'll just give an example and then conclude this talk. Here you see a face image, and according to the specific, according to 3 attribute classifiers, one for gender, one for age, and one for, let's say, race or ethnicity, the labels are produced here, female, middle-aged, Caucasian, and so the original label is 011. Here we're making some assumptions about the number of gender labels, the number of age labels, and the number of race labels. So now you can specify a target label by saying flipping 0 to 1, and now saying that you need a male, middle-aged, Caucasian. And so this image is transformed, but at the same time, the identity is preserved. And that is what this PrivacyNet does, because that is the name of the semi-adversarial network that I described in the previous slide. And so you can keep changing the target label. And so in some image space, it is moving around. But in each of these cases, the identity information is preserved from the perspective of face matchers, but the attributes are changed according to the labels associated with the C sub T, which is the target set of labels. So here you can see the input face image, which can be successfully used by a face matcher M, can be successfully used by a gender classifier G, by an age classifier A, and a race classifier R. But then by using PrivacyNet, you can disable certain attributes while retaining some other attributes. But in all cases, the matching capability is preserved, whereas other attributes are either confounded or they are retained. So some examples to show how this works. The middle image is what PrivacyNet does, and the extreme right is what a GAN does. And the scores, as you can see with the PrivacyNet, are still very high, suggesting that the identity information was not perturbed. Clearly, there are visual artifacts, something that we have been trying to work on. I now have a student who is trying to generate these images in such a way that the functionality is preserved, but also there is some degree of visual realism. We did a large number of experiments, and I won't go into those details, but this TIP paper from 2020 records a large number of experiments substantiating that this method is usable in order to impart soft biometric privacy to biometric images. So I'll stop there. I think I took more time than I wanted, with apologies to Anna and James. But these are some of the topics that we discussed today. I think we have a few minutes available for Q&A, and I'll be happy to answer questions if there are any from the audience. Once again, thank you. I look forward to your questions.